Welcome everyone to the linear regression session. So before I go into linear regression, what I'm going to cover is a slight overview on data mining technique classification. In data mining, broadly we classify techniques into two: supervised and unsupervised learning techniques. Okay, so what is supervised and unsupervised learning techniques? When we are analyzing data and the target information is provided to us. What I mean by target information is, if you are provided a series of data variables and one additional column is provided to you, which is we typically call target or the y variable. For example, when we build a linear equation, the linear equation is y is equal to alpha plus beta 1 x1 plus beta 2 x2. What we are trying to do, we are trying to establish a relationship between the y variable and x variables. For example, I want to say what is the monthly household expense of a family. Can I estimate monthly household expense of a family based on monthly household income? I can do. If someone's income is high, that family's expense is likely to be higher. Can I estimate the monthly household expense based upon number of families in that household, number of members in that family? I can do that, right? So here, if I give you three data points, one is household expense, family income, number of members in the family, I can establish a relation between expense as a function of income and family members. In this case, expense is my target because I am trying to estimate expense. The variable which you try to estimate is called as target variable. In a supervised learning technique, when you have the target provided, that becomes a supervised. In a data, when you have the target variable provided and you are analyzing that data, it becomes a supervised learning technique. Okay? Whereas in an unsupervised learning technique, I simply give you data. Say I simply give you transaction data of customers. There are certain customers who are coming to a retail outlet, and I simply provide you the transaction data of all these customers. And each transaction is mapped who has done the transaction. And I say you analyze these transactions. Now in that case, what you can do is, max what you can do is analyze the transaction and say which customer came how many times. What was the total amount they spent? What was the average amount of shopping they did per visit? Now here you are not trying to estimate anything. Here what you are trying to do is summarize the data given to you. And by summarizing data, you are trying to find some insight from the data. That is called a unsupervised learning technique. In a unsupervised learning technique, that there's no target. What you are trying to do is simply analyze data and derive some insight from that data. Okay? Broadly, simple example, if I give you these data points, which is shown on the screen as some cubes. Now here there are cubes which are colored as red and green. At the same time, these cubes are labeled as A and B. If I ask you to estimate something, can you do any estimation here? Can you come up with any business rule? No. What you can say is, you can only do some analysis. Some analysis basically would be some reporting. You can have some reporting saying that there are 6 cubes, 3 of them are red, 3 of them are green. So 50% of the cubes are red, 50% of the cubes are green. So I can do segmentation of this data as red cubes and green cubes. Or you can say, of the total number of cubes, there are 3 cubes labeled as A and 3 cubes labeled as B. So 50% of the cubes are A and 50% of the cubes are B. Again, this is summarization of data and segmentation. Now if I ask you to analyze and give some insight, what you can do is there are 2 segmentation you can do of this. One segmentation is I can segment the cubes based on color. The other is I can segment the cubes based upon character. Yeah. However, if I now add some additional information, which is basically all these cubes I give a label. So some of the cubes I have given a label saying epsilon class. Some of them I labeled as a lambda class. Now with respect to the label, I ask you to analyze the data. Now the data is, now this can be converted into a data format. This becomes my record number 1. This becomes my record number 2. This becomes my record number 3, 4, 5, 6. These are my 6 data points. Record 1 is labeled as epsilon class, record 2 is labeled as epsilon, record 3 is labeled as lambda, and so forth. And there are 2 attributes. One attribute is, record 1 attribute is red color, so color becomes one attribute, and the alphabet on that cube becomes its second attribute. Now I say you establish a relation between the label, which is lambda or alpha, lambda or epsilon, with respect to the attributes. What relation do you observe? No, what is the relationship that you observe now? No direct proportion. What relationship you observe between the class, which is lambda or epsilon, and the attributes? There are 2 attributes, which is A and B. Yes, so the relationship as it has come out, as is mentioned, the epsilon class, if color is red, then class is epsilon, else if color is green, class is lambda. Of the 2 attributes, one attribute is of no use now, because one attribute is able to help me say which class it belongs to. It is not necessary when you are given hundreds of variables, hundreds of predictor variables, or hundreds of attributes, all attributes to be used. Right? Here it is the clear thing that you are trying to establish a relation between the class and the label, and which you are getting. Make sense? So this is called a supervised learning technique. This is called supervised learning. Is this clear? The difference between supervised learning technique and unsupervised learning technique? When you do not have the target variable, it is simply called unsupervised. When you have a target variable, it is supervised. In a supervised learning technique, you try to establish a relation between the target and the attribute variables. In unsupervised learning technique, using the attributes, you try to find segments. Clustering is a technique which falls, clustering simply said segmentation. Segmentation is a technique which falls under the head supervised learning technique. Now, when we come to clustering falls under unsupervised learning technique. When we come to supervised learning technique, predictive analytics, which is I try to predict some value based upon certain inputs. It goes under the head supervised learning technique. Classification techniques, where I to classify something based upon certain attributes, it goes under the supervised learning technique. Yeah, so these points are clear. So in a linear regression, when we build a linear regression, typically what we try to do, we are trying to establish a relationship between the y variable and the x variable. The moment you say you are trying to estimate and build a relation between y and x, linear regression will fall under which head? Supervised learning technique. Yeah, make sense? Okay. Now let us understand what is linear regression. Linear regression, many people think, oh, linear regression, I have not done it. You all have done it. During your school days, we had linear equation. Simply put, linear equation is linear regression. Now get the confidence that you have done it. Okay, linear equation is linear regression. So with that, you start doing things. So in statistics, simple linear regression is an approach for modeling relationship between a scalar dependent variable. The y, we call it as a dependent variable. The target, statistically, in statistics term, the target variable is called dependent variable. I again repeat, in statistics, the target variable, which is our y, is called dependent variable. Let's take the example of household expense. Do you agree that the expense of a household whose income is high, the expense is high? The household whose income is low, their expense is also low. And when we talk about statistics, what we are talking about, what is a majorly identified phenomena, majorly observed phenomena. We are not talking about one stray case. We are not talking about one stray case where you will say, okay, there is one particular household, they completely live lavishly, but there is no family earning member. We are not talking about that kind of stray cases. We are talking generic, right? So it's very clear, expense is a function of income. Yeah. So can I say expense is dependent upon income of the family? The moment I say expense is dependent on income of the family, I hope this concept is clear. Why y variable is called a dependent variable. Yeah. Now the x variables are called independent variables or explanatory variable because they help you explain the y, and that's the reason the attributes are called independent variables or the attributes are called explanatory variables. Terminology first, because now I'm going to continuously use these terminologies, that's why get familiar with the terminology. Dependent variable, independent variable. Y is your dependent variable, x1, x2, x3, x4 are all independent. Okay. Now, in linear regression, typically there are two types of linear regression. One is called a simple linear regression. When you are trying to establish relation between y and one x variable, it is called a simple linear regression. And when you try to establish a relationship between y and multiple predictor variables, multiple explanatory variables, that is x1, x2, xn, it becomes a multiple linear regression. Clear? Now, this experimentation, I don't know how many of you did. It was typically done in 11th standard or 12th standard science stream. But if you are not from a science stream, basically in this experimentation, what was taught, we were given a ammeter. Ammeter is a device which measures the flow of current, how much of current is flowing. A device would be given which is called a voltmeter, which would measure the voltage, and we would be given a rack. In a rack there were many holders. In that holders we would put bulbs. Each bulb has got a certain wattage, so we know what is the resistance. So what we would do is we'll put a bulb, apply certain voltage, and then see what is the amount of current flowing through that electric circuit. Then we'll increase the number of bulbs, decrease the number of bulbs, and keep reading it. Okay, so we'll get some 10-15 readings. So in this, I know what is the voltage I'm applying, what is the resistance, the wattage bulbs I'm applying, I know that, and I is something which is unknown. So based upon voltage and resistance, the I value is decided. So we would put a plot of voltage as a relationship with I and resistance, and that relation would typically come this: the total current flowing through a circuit is directly proportional to the voltage you are applying and inversely proportional to resistance, which means if you have less resistance there will be more current, if you have more voltage there will be more current. And then we'll put and then this kind of a graph we will get. This is the relationship we are trying to find. So it's a linear relationship. So what it says is, for a given resistance, if I make, in this thing there are many three variables. If I make a resistance constant, if I keep increasing voltage, current also increases, and that relationship between the current and voltage is shown by this graph. So here the point is there is some proportionality, and that proportionality gives me a linear relation between them. Many a times when we have data, again I'm going back to the same example: household expense, household income, and household number of family members. If one family is having 50,000 as a household income monthly, assume there are 10 such families. All having 50,000 monthly household income. Will all the families will have 25,000 as a household expense? No. Right? So this kind of a proportionality relationship which I have shown here, that as voltage increases, current increases, I cannot have exactly proportional relationship, but I can have a relationship which will say how much expense will increase if given how much increase in income is there, right? So statistically what we are trying to find is a relationship, and that relationship will say, okay, this is a factor by which if income increases, then correspondingly we estimate that this much proportion of expense increase should be there. Okay, in linear equation we are trying to establish that kind of a relationship. Concept is clear? Okay. Let us take a simple example. I have given certain data points. The Excel file, complete Excel file is already shared. I have certain basic data points here, income and expense. And this income expense data I have plotted on the graph. First thing, monthly income is dependent variable or independent variable? Monthly income is independent variable. Independent variable, whenever you make graph, should be on x-axis. Expense is your dependent. The dependent variable should be on the y-axis. These are generally followed practices. Okay. So here I am trying to show that relationship, and it shows that for a given level, say for a given income level, there is one family whose expense is this much and other family whose expense is this much. Whereas there is another family whose income is lower but expense is still higher. It's quite possible. Some people live lavishly, some people live slightly conservatively, right? So what we are trying to do is we are trying to build a equation which is a line of best fit. Which is a line of best fit. What a line of best fit is? A line which will predict, estimate the value of expense for most of the cases correctly or nearly to the actual expense value. It may not be 100% correct, but it will be very near. Okay. So that is what I have to do in a linear equation. So this data, if that is my objective, what I could have done, this is the same graph. I could have say this is one of the plot which explains the relationship between income and expense. Now, do you agree this line on which I have put a red line on top of it is a line of best fit? Or would you say this yellow line on which I am now putting a red line is a line of best fit? Which of these two? I number this as 1 and I number this as 2. Which of the two lines is visually looking to you as a line of best fit? Amongst 1 and 2, which you feel is a line of better fitment? 2. Why you feel that line number 2 is a better fitment? This extension would be going like this. The reason, yes. So as we are getting the answer, the line 2 is passing through maximum number of data points. When a line 2 is going through maximum number of data points, what you can visually see for this data point, this is the error in my estimation. For this data point, this is the error in my estimation. For this data point, this is the error. But when you take this line 1, the error would start from here till here, because that is the gap between your estimate and the actual. Do you agree? Similarly, this is the gap between your this and this, but whereas if I take the second line, this is the error. This is the gap. The gap between your estimate and the actual is error. Yeah. So my objective is, of all these lines, 1, 2, 3, 4, 5, which the 5 lines I have done, I could have actually have infinite lines. Of these infinite lines, my objective is to find the line for which this gap across all the points is minimum. Because this gap is error. Do you want to maximize error or you want to minimize error? Minimize, right? So the line which goes through most of the points such that the difference between your estimate and the corresponding dot taken across all of the points, summation across all of the points is minimum. So I need some function, I need some measure by which I can say this is the line of best fit. And that measure is basically how far off you are from your actual. How far off the estimate is from the actual. Yeah. So the way this entire linear equation, linear regression, line of best fit is done. Assume, I'm saying assume, okay? As of now, this is not a line of best fit. Assume this is a line of fit that you are trying to achieve. For this point, this is my error. Now the error would be ym. Ym is actually the actual value of y for this data point. And ym hat is basically what you have predicted based upon your line of best fitment. This is the error of this data point. This error, say I'm doing ym minus ym hat, so this will be positive error. Agreed? Because ym is higher value, we can see. Now for this data point, I can similarly calculate ym minus ym hat. Ym in this case would be, let me say not ym, let me say this as yn, because it's another data point. And this corresponding value, I'll say yn hat. So this difference will be negative. If I do simply summation of these positives and negatives, if I do simply the summation of these positive and negative errors across all data points, it is quite possible that you may get a line of best fit which is not a best fitment, because it is quite possible the error because of one term which is an outlier here, something here, will have a huge error, and that nullifies many small errors on the downside. So the right approach of getting error is not to take this difference directly, but to square this difference. This is the gap, but when you compute error, you have to square it. By squaring, what do you achieve? You have values as positive. The moment you square the values, negative square is minus 1 square is 1. So what will happen is all of these error terms which are on the negative side and which are on the positive side, the moment you square them, they will become positive, and then you add it. Now your objective is to have a line of best fit which minimize this summation of error squares. Okay, we will not go into deep calculus. We are definitely not going to go into deep calculus. Now this SSE is equal to summation of error squares. Okay, and this error square is yi minus yi hat square. Just as I explained, if I can compute this error for one of the point, then I can compute error for this, then I can compute error for this, I can compute error for this, and then add up all of these square terms. When you add up these square terms, we call it summation, and that summation is represented by this symbol. Okay, so this is what the summation is. A linear equation format, the y hat value is basically arrived using this kind of equation. This is a linear equation format. Y is equal to alpha plus beta 1 x1, or y is equal to a plus bx, or y is equal to b0 plus b1 x1, whatever you say. So I can replace this y hat here, and then I can run calculus. Calculus is basically a derivatives, integration, limits. All these concepts are part of derivative. All this part are part of calculus. I can run a calculus to arrive the equation such that this error term is minimized. We are not supposed to go into calculus. Okay. If I solve that, I can get this equation, and by solving that, I can get this B0 is basically my intercept. This B0 is my intercept, and this B1 is my beta for the x1 variable. Okay. What at a conceptual level you have to understand? At a conceptual level you have to understand is we are trying to establish a equation between dependent variable and the independent variable, where in this case the dependent variable is a constant, dependent variable is a continuous variable, scalar variable, and x is another independent variable between which you are trying to establish the equation. The tool which you are going to use, R, SAS, KXCN, Vecka, MATLAB, whichever tool, once you provide the data, you have to simply say which variable is your y variable and which your x variables. The tool will do all the calculus in the background. It will run all the regression steps in the background and give you the equation. Yeah. So this is how the line of best fit is arrived. Major point here is you have to understand is there is an error which we are trying to minimize, and by minimizing the error, the line which has got the minimum error is called the line of best fit. Okay. So now let's go to R and start doing the linear equation. Okay. So just from a layman's perspective, let us try to, I am trying to explain things with respect to from the point of view of a layman only. This part you're not supposed to understand, the calculus part. From a layman's point of view, what is happening in the background, I'm not supposed to bother. What you have to understand is you are trying to establish a relationship between y and x. What you have to understand is y dependent on x? From your business understanding, from your understanding of data, if you feel y is dependent on x, then and y is continuous. Basically it should not mean y has got only two classes as I took in supervised and unsupervised. Okay. Typically y, when you are using a linear equation, linear regression, typically y is continuous, which means it has got many levels, many values. It is a scalar, not just two levels, 1 and 0, or epsilon and lambda. So yeah, first point is that. Second is, from your business understanding, y has got a relation with x, and you are now trying to get that relationship. Okay. Third is, the equation format of a linear regression is y is equal to alpha plus beta 1 x1 plus beta 2x2 plus beta 3x3 dot 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 beta n xn. What it means is a certain fraction of x1 or certain multiplier of x1, if I do add it to x2 by some multiplier plus x3 with some multiplier, when I add this and a constant which is the initial b0 or alpha, that summation is equal to y, and that y is basically estimate. As we discussed in the initial example, expense of a household, if there are 10 families each having 50,000 income, it is not necessary that all of them will have 25,000 as expense. But what the equation is going to do, it will try and find a line of best fit. Now if there are only 10 data points and I know for these families the expenses, someone having 10,000, someone having 20,000, 30,000, 40,000, 20,000, 30,000, I'll get an average of these 10 data points, and I can say, because all of them have the same income level, someone but have 10,000, some 20, some 30. So I'll take an average of this and say more or less everyone would have a expense of 28,365 if that is the average. Okay, but here the point was X value was 50,000 for everyone. But if when I have many household, everyone will not be at 50,000 income level. Some will be at 55, 56, 58. So what I have to do is find out average for each of these segments. But this average for each of these segments has to be determined in a way which is continuous. Because again the income levels, someone will have 50,000 and someone will have 50,001 rupee. Someone will have 52,000. Someone will have 53,000. And in 52,000 there will be only one record. In 53,000 there will be two records or zero records. So I have to make an equation which is continuous. Yeah. And more of this, as we solve the practical problem, it will get much more clear that how this linear equation is works. Yeah. So let us take a simple example, and even the data is so intuitive. If you solve this, you will be then able to relate to other problem statements which are of similar nature. Yeah. So let's start with the linear regression. All of you just open the linear regression code file that I have given. And the first step, what you have to do is set your working directory to the folder where the data file is stored. Okay. So the data file which I have shared, put in some folder and set your working directory. For me, the data file is in DK2 analytics data file. That's my set working directory. I have set at that level. Okay. Okay. So I have set my working directory, and then I'll import the data income expense data.csv which is given to you and view. Let us quickly understand what data has been given to you. There are some 50 observations which is given. So basically a survey has been done for households, and their income data has been asked. What is the approximate income? What is their approximate expense for the month? How many members stay in that family, in that household? Are they staying on EMI or a rental basis? If they are paying EMI, what is the EMI they are paying every month? And if it is on a rental basis, what is the rent that is going out? And what is the total annual income of the family? Okay. So these are the data points that we have, and overall 50 observations. What we have to do is we have to establish a relation between expense and other predictor variables. Expense is my dependent variable. Monthly household income, number of family members, EMI or rent, and annual household income. These are all my independent variables. Okay. So first thing, what I'll do is try to build a simple linear regression. Though my objective is to build a estimate expense with respect to all other variables. But first I will cover a simple linear regression and then I will cover the concept of multiple linear regression. So let's quickly do a plot of a scatter plot. So the code is given. I'm not explaining the plot code. So let's run the plot. Using the plot, I'm building a scatter plot. Okay, so this is my scatter plot. Zoom. Okay, so this is a graph. Here we can see that income and expense, the dotted things which I showed you in the presentation. What we'll do is we'll put a AB line. What is this AB line? Why is it called AB line? The linear equation is y is equal to a plus bx, right? So AB line is to say a plus bx. So again, AB line, I'm using a linear model, LM. I'm using LM function which will help me build a linear model. In LM, expense is my target. So I'm saying I want to establish a function which is expense as a function of income. So if you see that this code can be split into multiple components. This line which I have now selected is to build a linear model as a function between expense and income. This model I am trying to show on the graph as a AB line. Okay, so let us run this and this I get a AB line. This is just a visual plot to get a feel of the relationship. Not much to say. Now let me run the same linear model and try the summary. So I'm running linear model LM as a function of LM function where expense, I'm trying to estimate expense as a function of income, and both the expense and income variable is part of my income underscore exp data frame. So this one line equation, one line of function builds your linear model. All the regression steps trying to fit a line of best fitment all happening in the background. We should just know overview and we should know the concept element that a line of best fit is done by minimizing the error. Okay. Practically, we are not going to take the entire Excel data and start working out things in Excel. We are going to use some tools. Yeah. So this is my line of best fit. Let me see what is this intercept and coefficient, beta coefficient. This intercept is coming as 6319. This intercept is coming as 6319 and the beta coefficient is coming as 0.3008. So basically the equation is, what this means is y is equal to, basically the other way of putting this same thing is expense is equal to 6319 plus 0.3008 times income. This is what this intercept and coefficient is trying to say. If this is what the equation is trying to say, what is this intercept meaning? What is the interpretation What is the interpretation of this 6319? The interpretation of the intercept 6319 is, if a household does not have any income, can they survive without any expense? So in this, what it is saying that bare minimum any household will spend about 6,319 rupees every month, irrespective of whether they have income or not. And that is fact. For livelihood, some expense will always be there, right? Irrespective of whether you are having an income or not. And this is saying, this is what the intercept is saying. What is 0.3008? Here, in this case, it says that 30% of the income goes as expense. So if some household's income is 10,000, the expense of that household will be 6,319 plus 3,000, because bare minimum anyone will require 6,300 to spend, and because they have got some more income, they will try to live slightly better off than someone who don't have any income. Yeah. So this is a simple linear regression. Make sense? Is the concept clear? Okay. Now, if this is my simple linear regression, what I have to see? How good is the model? Once you have built a model, this is a simple linear regression model. You have to, any model you build, you always have to see the efficiency of the model, how good the model is. Okay. So there has to be some measure by which you can find out how good the model is. Yeah. Okay. There is one family with an income of 5,000. How this equation satisfy that? Faz, when I started off, I gave an example. It is quite possible that someone has got only 10,000 income, but his expense can be 1 lakh also. There may be stray cases where people live larger than life. They spend more. The objective of statistics is not to predict each and every case correct. The objective of statistical models is not to estimate value of each and every case correct. The objective of the model is to estimate most of the cases correct or closer to their actual. You cannot be 100% correct almost all the time. Okay. So now let us understand how we go about evaluating this model. To evaluate the model, there is a measure called R square. There is a measure called R square, and that is called coefficient of determination. To understand what is coefficient of determination, let us first understand the definition. In statistics, coefficient of determination is denoted by R squared, and it is a number that indicates the proportion of the variance in the dependent variable that is predictable from the independent variable. First thing, proportion of variance in the independent variable. This element. First, we have to now understand the concept of variance in the dependent variable. What is variance? Dispersion. Variance is a measure of dispersion. Proportion of the variance in the dependent variable. Now, which variable is dependent in our case? Dependent variable, expense. Are all the customer, not all the household, is all the household having same expense? There are some households having 5k as expense, and there are some households who has 50k as expense, monthly expense, which means there is a wide difference in the expense of each household. How can I quantify how much is the difference in expense of each household? Can I have some measure? Can I have some measure by which I can say whether the expense is too widespread amongst the household, or it is too much close to each other amongst the household? That measure is called variance. Variance is a way to measure how dispersed the data is. Let us take a simple example. If I go to a first standard school class, I go to a school and first standard class, what will be the age of students in that class? 5 and 6. Everyone agree? Some will be 5 year 1 month, some will be 5 year 2 months, some will be 5 year 3 months, some will be 5 year 5 years 6 months, some will be 6 years. Is the data too dispersed if I take 50 students and have their age up to month level, 5 year 1 month, 5 year 2 months, 6 year? Is there much dispersion? There's not much dispersion. Okay. Now let us go, now move from first standard, and now let us go to MBA. MBA first year students. What will be the age? Someone will be 22, someone will be 23, someone will even be 40. Do you agree? 40. Do you agree? So again I take 50 students and take their age. So 22, 23, 24, 28, 30, 36, 40. Can you see that there is a dispersion? Dispersion in terms of years or months? Now you take it in year terms or months term, whatever month terms you want to. The range is the so there is a wide range. There is a wide range. Now how can I quantify this dispersion in one numeric term? Can I quantify it in one index? And that one index is variance or standard deviation. Variance is nothing but square of standard deviation. Okay. So concept of dispersion, the data is more spread or data is less spread. When the data is more spread, I'll say it is higher variance. When the data is less spread, I'll say the data has less variance. Yeah. Variance is a measure of how much the data points are away from the average. And the formula for variance is summation of each data point minus the mean. So summation of y minus y hat. Y hat is the average. So when I take 50 students, I take average of all the 50 students. That becomes y hat. And each student's age is y. So if I take first student, the age minus the average, the whole squared. I take second student, that value I'll again call it y. Typically that's the way you say. What happens is each record wise the y value will keep changing and y hat is the average. Summation of y minus y hat the whole squared divided by n is your variance. And if I do square root of this term, it is called standard deviation. And if this data that you have derived, statistically if you have derived this data points from a population, you have taken a sample from a population, then the formula is y minus y hat the whole squared divided by n minus 1. That will be the formula for variance. Again the point is, formula is not important. Formula is not important. Is the concept clear? Variance is a measure by which I can say how dispersed the data is. If there is a high variance, which means data is more dispersed. If there is low dispersion, the variance will be low. Okay. So first, let's understand this variance concept. Now, let us take this example forward. I'll take another example to explain how R squared is used. Let us take employees of a company. Will each employee have the same salary? No. Within a department, will each employee have the same salary? No. Within a given role, if there are in a given role, will each employee have same salary? No. And the moment you come to know the salary of another employee and which is higher, what do? You immediately retaliate and go to your HR and say, why is his salary higher than yours? But if your salary, you come to know your salary is higher than his or her, basically the point is each employee don't get the same salary, right? Now there is again a variance. Someone gets less, someone gets more. Assume I take 50 employees from a same department doing more or less having the same designation, and I know their salaries are different. But now I start adding some knowledge and some information additional. So assume there are 10 different salary levels. Some employees are getting 20,000, some are getting 25,000, some are getting 30,000, some are getting 35, 40 and so forth. Now I start putting some information to this data point saying the 50 employees whom I have considered, of the 50, 30 are MBAs. Basically post-graduation. 10 have done PhDs and 20 have done only graduation, either engineering or commerce. And now I try and find a relationship and see that the 30 who are MBAs, they have got a certain income which is slightly or more higher than the graduates, and the PhDs have got much higher salary. So what I am trying to do, I am trying to now explain why is this income level different for these 50 people. Yes, the amount of explanation I can do based upon this is called variance explained. Someone has got higher income, someone has got lower income, someone has got moderate income. But when I now say the people who have got higher income, the reason why they are far away from the mean is because they are PhDs. Someone who is slightly above the mean is because they are the MBAs, and someone who is below are graduates. Right? So what I'm saying is, with this information, I'm now able to explain why someone has got higher income and someone has got lower income. And the extent to which I am able to explain is called variance explained. Now all the 30 MBAs, will they have the same income? No. Again there will be some difference in their incomes. And that difference in income is the variance unexplained. Based upon MBA attribute or the qualification attribute, that variance is still not explained. And that is called variance unexplained. The amount of variance that you are able to explain is called coefficient of determination. And the amount of variance which you are still not able to explain is residual error. Are you getting the point? The amount of variance by that information, which is the qualification, you are able to explain why their salaries are different, is called variance explained. And that percentage of variance which you are able to explain as a variance of the whole is called coefficient of determination. And what you are not able to explain is called residual error. Okay? So with that concept, if that concept is clear, so let us understand the calculations. So first thing what we are going to do is, we are going to compute the variance of expense. Okay? To compute the variance of expense, first thing I need to know what is the mean. So I have to first compute what is the mean. So let me put mean. Mean is basically average. So I'll use the average function and then, so what this shows is average of all these data points, 50 data points that I have, that average is coming out to be 18,818, which means average expense of a household is 18,818. So if I don't give you any information, in absence of any information, if you have to make any statement, what is the expense of a household, what you will say? Average expense of a household is about 20,000 rupees. That is a generic statement that we can make. But now the question is, if average is 20,000, there are some people who are 50,000 expense, there are some people who are 10,000 also. So why is there some people 20,000 and why some people 50,000 and why someone 10,000? And if there is a difference, then there is a variance. Yeah. So let us first compute the variance of the variable, which is expense. Okay. The formula for variance is y minus is basically summation. So summation of y minus y hat. Okay, I'm just typing it. The whole squared divided by n minus n or n minus 1. But here in this case I know this is the entire population, so I can divide it by n. Okay, so this is the formula. So first I have to get the y minus y hat. Okay, so y minus y hat is what? This minus average. Yeah, what is average? Average is here. So I'll just make it f4. Okay, I'll make it a constant. So I've got this formula, y minus y hat for all of them. But actually what I want is y minus y hat the whole squared. So y minus y hat the whole squared. So what I can do is simply this squared. Yeah. This is a square term. Yeah. What is the formula of standard deviation or variance? Summation of the square terms. So all these square terms summation I have to take. Yeah. I take summation of all of this, divide by n. So n is how many? 50. So variance is equal to sum divided by 50. So this is variance. And what is standard deviation? Is equal to square root of variance. So this is square root of variance. So basically, how is standard deviation used? The way standard deviation is used, I know this is mean 18,000. If I do 18,000 plus or minus one standard deviation, what it will give me? 65-66% of the people, of the households, their expense will be between, the way standard deviations are used, if I do plus standard deviation and on the other side I do minus standard deviation, I can say approximately 65-66% of the people, of the households, their expense will be between 68,000 to 30,700. If I have to say at what is the expense range for 90% of the people, approximately 90%, I'll have to do 2 standard deviation. If I have to go about 95, 99 percentile, then there is a 3 standard deviation, 3.6 standard deviation. So there is some, again, formulas. Okay, plus or minus 1 standard deviation, it will cover 68% of the data points. Plus or minus 2 standard deviation, it will cover approximately 90% of the data points, will be in that range. Okay, now this is my standard deviation. If I know income, can I predict the expense? Yes. What is the equation that we got for that expense? This was the equation, 6319 plus 0.3008. Yeah. So I'll take this 6319. I'll put it here and 0.3008 plus 0.3008 time income. In absence of any information, I make a generic statement, all household has expense of 18,800. And because of that, for this particular household, my estimate was wrong by 10,818. For this it was wrong by 11,818. For this it was wrong by 14,318. Now let us see how close my estimate can be if I use this above equation. So I'll have 6319.1018 plus 0.3008 times income. So my estimate, I'll round it off. My estimate is 7,823 for this particular household. So 8,000 is actual expense. My estimate is 7,823, which is very close. Yeah, definitely for some it will not be that close. For some it would be far off. For the second one, actually 7,000, I estimated 8,000. So my error, I'll directly take square. I'll directly take the square term, or let me take error. So my error is this much. Can we see that? Can we see that our error based upon the model, for this it was 10,888, now it is just 177. Each error terms are lower compared to what was actual most of the places. So by building the model and then estimating the expense, I am now, rather than saying everyone has got 10,818 as an expense, which is the average, I'm now saying this household has got 7,823, this household has got 8,124, this household has got 9,327, and so forth. Yeah. By doing that, I have reduced my error. I need to now quantify by what percentage I have reduced the error. Yeah. Do you agree this 177, the gap between my estimate of 7,823 and this 8,000 is 1,177. This is still unexplained, right? Whereas for this case, I have estimated 10,530, actual is 8,000. I have estimated higher, 2,530. Again, the gap is unexplained. Why that household is having less expense as compared to what has been estimated? It is unexplained. Can I say this is a unexplained error? Yeah. So what we are going to do again, we'll do square of this term. Yeah. So unexplained error square. Let me do sum of this. This number also, let me put the comma formatting. This was the total variance of the expense variable, and this is the unexplained component. The difference between this and this is explained. Oh, sorry. Here I have done divided by 50. So let me do this also, divide by 50. Or actually I can remove the divide by 50 both sides, but let me do this also, divide by 50. Okay. So can I say this much gap is already explained? This is explained. Let me take a ratio of this divided by total. Yeah. See, this is the unexplained error total, or rather than saying a total unexplained error. Of that, this ratio, I am again doing this total unexplained error divided by total variance of the expense variable is unexplained percentage. Yeah. This much proportion is unexplained. How much is explained? Is 1 minus this. By using income information, I have been able to estimate expenses of many households correctly to some extent. So what it says is 42% of the expense I have been able to explain using income information, and this explained variance is called R squared, coefficient of determination, because you are able to determine. Again, going back to the same example, salaries in a department are not same. Now when you start putting qualification, then you find out why are many people getting higher salaries and why are many people getting lower salaries. So basically you are now able to say the reason why who are getting higher salary, but you are not still able to justify within a given qualification why is still people getting different salaries, and that is called unexplained. Similarly, when I built a simple linear model using income to predict estimate expense, I have been able to explain 42% of the reason why different households has got different expense level, but still I have not been able to explain the 58% of the data. Yeah, does this make sense? So let us see what is the R squared for our model. I have done all the calculation. Let us see the R for our model, 42.14, and this is the number that we got, right? The entire calculation is what I have shown in Excel. All this calculation you did not know, but the concept and the science behind it is what you have to know. What R square is saying is what is this number interpretation? English statement to interpret this is 42% of the variance in expense is explained by income or by the model that we have built using income variable. Make sense? Can I explain the remaining 58% of the variance in expense also? Is it possible? Is it possible to explain the variance in the remaining 58% of the variance which is still unexplained? Can I explain that? Can I explain that somehow? It's possible. Do you agree that expense of a household is just not a function of income? It's a function of something else also. Let us take example. Two families, one family is just basically a husband and wife, no children's, double income, no kid. Okay, both of them earning 100,000, lakh rupee. Now there is another family where they have got two kids. Again, the income of both of the couple is basically lakh rupee. And now let's take one more family, which is like a joint family, where husband, wife, two kids, and their parents. So total 6 members are there, assume. So one family has got 2 members, another has got 4 members, another has got 6 members. Total income in each of the family is same, 2 lakhs. Will their expense be different? Yes. So what happened when I tried to establish a relation between income and expense? I was trying to predict expense based on income. And for all of them, once I get an equation, for all of them, my estimate using the model will come out 36,000 rupees. Okay. But still someone will have 36, someone will have 60, and someone will have 1 lakh rupee as expense. So not using my model, it will come 66,000, not 36,000. This model, it will come 66,300 rupees something. So, but someone will have 66,300, one will have 1 lakh, and other may have 1,50,000. This range, which is not explained, can I explain it? Yes. If I now bring in additional attribute, which is number of family members. Yeah. So what multiple linear regression says that when you're trying to predict a y, it is not necessary that y is just a function of one variable. It is quite possible y is a function of multiple variables, and that's the reason why we require multiple linear regression. Many of the problems cannot simply be solved by a simple linear regression. Yeah. So let's try solving this model using a multiple linear regression. Just before we go into multiple linear regression, let us understand one more element. I have explained R square. Okay, so R square, if you run this summary function, you will get the complete statistics of the model. So let me quickly run a summary function. Summary of the linear model. This is the complete statistics of the linear model. So here it shows you estimate, which is 6,319. The and this is the 6,319 is the intercept, and this is the beta. Now p-value. What is p-value? P-value is basically comes in hypothesis testing. Okay. So let's understand what is hypothesis testing. In hypothesis testing, you are trying to validate a hypothesis. Now, the hypothesis here was expense is a function of income. So what we are saying that our hypothesis is expense level of a household varies depending upon their income levels. Yeah. If that is a hypothesis that you are trying to prove, a hypothesis requires two hypothesis statements. One is called a null hypothesis. Null hypothesis statement is status quo, or the other way to put is y is not a function of x. Yeah. So the null hypothesis is y is not a function of x. And the alternate hypothesis statement will be y is a function of x. That is what null hypothesis testing requires. In a hypothesis testing, you have to make two hypothesis statement. One is called null hypothesis. Null hypothesis statement is y, which in our case is expense, is not a function of income. And the alternate hypothesis statement will be y is a function of x, which is y is dependent on income. The way hypothesis testings are interpreted, it is based upon p-value, which is the confidence value. And again, to understand the hypothesis, what you have to set your own alpha, which is the threshold p-value you have to set. Say you have set a threshold p-value as 0.05. What 0.05 threshold means is, my alternate hypothesis, expense is dependent on income. I'll accept this hypothesis statement if I am confident 95% or above. When you set threshold p-value as a benchmark baseline for your own hypothesis validation, you are saying alpha is equal to 0.05, which means the alternate hypothesis confidence level is 1 minus 0.05. That is, you will accept the alternate hypothesis at 95% confidence or above. In our case, what is the p-value? 3.397 e raised to minus 07, which means the alternate hypothesis confidence value is 1 minus 0.6 times 03, which is 99.9 times 99.6 times 97, 99.9999997. At that confidence, it is being validated that expense is a function of income. Will you accept the hypothesis? Yes. Which means this model is a significant model. This model is a significant model. Yeah. So that is on the hypothesis testing part. Now let us take it forward to multiple linear regression. So here I built this model using one variable, income. There were other variables available with me, and we saw that R squared of this single variable model was 42, which means 42% of the variance of expense has been explained. Let me just add one variable, dollar number of family members. Okay, so I'm building this. I'm now building a model where I'm saying expense is a function of income and expense is a function of family members also. So when I just run this, the model is built. If I have to get the intercepts and all the p-values and other statistics, let me just quickly run summary. When you run this summary, it just says linear model you have built between this coefficient. Now when you have got this summary, the intercept coefficient don't have much meaning now. The intercept coefficient has meaning only when you are building a model which is between y and x single variable. Now this intercept you cannot interpret. Okay, and this is the beta of this and this is the beta of this. Let me focus here now on R squared. R squared earlier was 0.42. Now what is the R squared? 0.5736. 0.5736. What does 0.5736 mean? (57.36%) of the variance in expense is explained. With income, I was only able to explain 42. Now I am able to explain 57. If you are going to take this equation, y is equal to, y means expense. Expense is equal to minus 4.0 e raised to 03 plus 0.2101 times income plus 3477 times family members. If you are going to take this equation and go to Excel, put this equation here instead of this equation. You replace this equation and calculate. You will see this unexplained error will go down, will further go down. Yeah. And as you keep adding attributes by which you are able to estimate the expense more properly, this unexplained error will keep going down. As your unexplained error keeps going down, your model will become more perfect. As model becomes more perfect, your ability to determine the values, predict the values goes higher, and as it goes higher, your R square, which is coefficient of determination, will keep increasing. Agreed? Okay. So let us come back to let us now start with the multiple. I just executed the multiple linear regression with one additional variable and showed that as you increase the variables, R squared, and it's not necessary that if you increase variables by adding any variable, R squared will increase. If you are adding variable which has a relationship with the dependent variable, only then R squared and the model performance will improve. If you add a variable which don't have a relationship and you just simply add, it is not going to impact. Yeah. So now what I'm going to do is I'm going to build this model multiple linear model with all variables. Okay, rather than adding one variable at a time. Now before I do that, let me just run a correlation. What is correlation? What does correlation mean? If there is a correlation between two variables, what it means is as value of one variable increases, the value of the other variable will also increase or decrease depending upon how correlated they are. So now correlation, what is the range of correlation? What is the range of correlation? -1 to +1. The range of correlation is -1 to +1. -1 indicates perfect inverse correlation, which means X will increase, Y will decrease. +1 indicates perfect positive correlation. X increases, Y will also increase. What does 0 indicate?
No change, no relation.
No correlation, which means Y will not increase or decrease based upon X. Now, if I say correlation between X and Y is 0, does it imply absence of any functional relationship? If I say correlation between X and Y is 0, does it indicate absence of any functional relationship? Absence of correlation indicates that there does not exist linear relationship. Absence of correlation, that is zero correlation, does not mean absence of any other type of functional correlation. Let us take a simple example for this. This is my x-axis and y-axis. Okay, this is my x and y-axis. And I've got certain data points which are like this. Is there any relation between x dots and the y, all these dots? Because the dots are plotted on x-axis and y-axis. This is how my data is. Is there any relationship between y and x? There is a relationship. There is a relationship. Can you see these dots are like a circle? This is a circumference of the circle. When it's a circumference of the circle, the x values across all of them and y is like 2 pi r relationship. Right? So there is a relationship between these dots. But not a linear relationship. If I take these data points, correlation will be 0. But as I said again, absence of correlation does not mean absence of any other type of relationship. There are multiple types of polynomial relationship. There's different types of relationships, functional relationships. So here they're still associated. Only thing is, zero correlation means no linear relationship. Yeah. So let's first see correlation between the independent variables. Okay. To get a correlation between independent variable, the step is simple. You simply have to say core and the independent variables, or all the variables that you want. So I'll do correlation between all independent and dependent variable, including expense. Okay. This is a simple output that I have got. Monthly income with respect to monthly income, obviously correlation has to be 1. Yeah. Monthly expense with respect to income, 0.64. Yeah. Which means it's a slightly good correlation. This 0.64 should not be interpreted as expense is equal to 0.6 times income. Okay, it just says that 0.6 just says that it's slightly better of correlation than the correlation between family members and income is 0.44. What it just says that income and family members are not very correlated. The interpretation is logical. Number of family members in a household is not a function of their income level. Double income, no kid. Right? So this number has to be interpreted from those perspective. EMI and income does not have a relationship. There are many people who have got high income. It is not necessary that they will not take house on a EMI. Right? It's not that they will not take house on a loan. So it's showing 0.03, which means people taking house on loan or not taking house on a loan is nowhere a function of income. Yeah. So it has to be interpreted from that perspective. It should not be saying that EMI is equal to 0.03 times income. No, that is not what it is trying to say. Yeah. Annual income and monthly income, 0.97. Make sense? Perfect correlation, right? Annual income is typically 12 times monthly income plus bonus elements, right? As such, some amount of it cannot be 100% perfect. If annual income and monthly income was exactly 12 multiple, it would have come as 1. This is what the interpretation of correlation is. Does it make sense? Yeah. Okay. So if we have this interpretation clear, okay. So let's move forward from correlation. Why is this correlation concept important? We'll now quickly see. I've got a linear model, multiple linear model, income, family members, EMI or rent, plus let me add the variable annual variable also. So now I'm building a model which is a multiple linear model. We already built one multiple linear model where we had expense as a function of income and family members, and we saw R square improved. Now I'm building a multiple linear model where I'm building expense as a function of monthly income, family members, EMI and annual income. Yeah, let me run that. Okay, my model is built. Let me do summary of it. Now the summary of it is this. Let let me get this coefficients better. This is slightly okay. Now here, everyone just pay attention. What is this equation saying? These intercepts and beta saying expense is equal to 5 raised to 3. So minus 5124 something plus 0.40 monthly income plus 3224 times family members plus 0.6 times EMI plus minus e raised to minus O2 0.0166 times annual income. This is the equation. Logically tell me, if monthly income increases, expense will increase. If monthly income increases, expense has to increase, which means the beta has to be a positive number. Agreed? If number of family members increases, the expense has to increase, which means the beta of family member also should be positive. Gopal, what it simply means, if beta is negative, this number instead of 3224, if this number would have come as minus 3224, what it simply means is with each increase in family member, the expense of the family would reduce by 3224 if beta is negative. Does that make sense? How are you saying in a way, if with each increase in family members, if this beta would be negative, not positive, then what it would mean is expense of the family would reduce with each increase in family member increase. So the point I'm trying to make, the way to understand the betas, I would request you to be attentive. The way to interpret the betas is, if the beta is positive, what it says, if the value of that variable increase, the y, which is expense in this case, will increase. Now just assume if this beta, instead of coming as 3224, it would have come as minus 3224. Does that make sense? Which means my family members increases, then I am saying the model is saying as family members increases, the expense of family reduces. Illogical statement, right? This is how the betas are to be interpreted. This is where the sign of each beta is now important. Okay, so here we agree that beta of family members should also increase. If someone is staying on EMI or rent, will that family member's expense be higher? Yes. So again, the beta for this variable should be positive. If a family's annual income is high, then their expense should also be high. Yes. But the beta is coming as negative. But the beta is coming negative, minus 0.0166. Does that make sense? If the beta minus 0.0166 is not making sense, then there is a problem with the model. Do you agree? And this problem is called multicollinearity. This problem is called multicollinearity. What is multicollinearity? Let me explain the problem of multicollinearity. Okay, definition is not there. Uh, Multicollinearity is when two or more variables, when two or more variables which are correlated are trying to predict the same phenomena, you end up with a problem of multicollinearity. For example, can I derive annual income as a function of monthly income? When two or more predictor variable or independent variables are correlated and they are trying to predict the same phenomena, which is in this case expense, you will end up with a problem which is called multicollinearity. Okay, do you agree? If you want to understand that slightly better, let us go back. Instead of building a model where I am using many variables, I'll use monthly expense as a function of monthly income and annual income. Yeah. So let us build this model. And now let us see the coefficients of this model. The coefficient here, if you see 0.59, it makes sense. And this is minus 0.02. Okay. So let me take these data points in Excel. So this model is saying expense is equal to 6203 plus 0.59, so 0.598, I'll just put as zero point 0.6, okay, times monthly income plus bracket minus 0.025 times annual income. Okay, this is what the equation is. Let us build this model with only one variable, which is monthly income. Okay, I remove this annual income and let me see this model. Sorry, I should just get the coefficient. This is the equation. This equation is expense is equal to 6319 plus 0.30 times monthly income. These are the two equations we are getting. Yeah. Let me take this equation down. Can I say theoretically we saw correlation between annual income and monthly income was coming as 0.97, and I know that annual income is approximately equal to 12 times monthly income plus bonus. Yeah. So in this equation, can I replace this annual income as 12 times monthly income? I can do that. Yeah. If I can do that, expense will become equal to 6203 plus 0.6 times monthly income plus bracket minus 0.025 times 12 monthly income to 12 into minus 0.025 minus 0.25, sorry, this has to be 0.025. So let us just separately do that calculation. 12 star 0.025, this is 0.3. Let me see how at decimal, one decimal place also, 0.30. So I can replace this part, which is minus 0.025 multiply star 12 and by 0.3, right? So this equation will become expense is equal to 6203 plus 0.6 monthly income plus, sorry, minus, because minus 0.025 into 12. So minus 0.3 monthly income. 0.6 monthly income minus 0.3 monthly income is what? 0.3 monthly income. So this equation becomes equal to 6203 plus 0.3 monthly income. This equation is same as this equation. Let me copy this equation also here, which was single variable model. Can you see these two equations are close to same? Yeah. So basically, if one variable, when there is a correlation, what correlation says is one variable can be derived from other. Now I have got two variables which are correlated, and I'm taking both the correlated variable to predict expense. Is there necessary to take both monthly income and annual income? And when you have these kind of correlated variables to predict a event, you end up with the problem of multicollinearity, and because of the problem of multicollinearity, the sign of this variable, which was annual income, came wrong. Because logically, if annual income increases, monthly expense has to increase. But the negative sign is saying that annual income increases, monthly expense decreases. And this kind of problem is called multicollinearity. I again define when two or more independent variables are correlated. In our case, monthly income and annual income, they were correlated. And these correlated variables are used to predict a particular event, in this case expense. Then you will have the problem of multicollinearity. And when there is a problem of multicollinearity, you will see that one of the two variables most often will have an unstable beta. In this case, the beta of annual income was coming as negative. And it is quite possible the instability may not be remaining to this level. If I do a small change in data, it may so happen monthly income may become negative beta and annual income may become positive beta. That's the problem. That's the problem. That by change of, if I remove 10 records out of it and again run a regression, it is quite possible monthly income may end up with negative beta and annual income may end up with a positive beta. Again, because there is a linear equation between them. There is a relation between them, and that relationship is automatically going to adjust. So when there is a problem of multicollinearity, the model as a overall will be stable, but the independent variables their betas may not be stable. So I can go ahead and use that model and make prediction. All estimates will come right. All predictions will be more or less good. Only thing is, when I go at independent variables, the betas of those independent variable may not make sense. Or the other way I'll put, the independent variable betas will not be stable. Okay. Let us quickly take a break. Okay. So we just saw what is the problem of multicollinearity, and we defined that when two or more correlated variables try to define the same event, we end up with the problem of multicollinearity. And here we could clearly see that because of multicollinearity problem, if I pass monthly income and annual income both the variables, annual income can be derived from monthly income, or monthly income can be derived from annual income. As a result, I don't require both the variables. So to avoid the problem of multicollinearity in your model, what we have to do is we have to remove the correlated variables. But before I can remove the correlated variables, in this case it was very simple, monthly income and annual income, and because we know the data. But most of the time we will not have these relationship very easily known. So how do I figure out my data has got a multicollinearity problem? So there is a very simple element which is what we compute is variance inflation factor. Okay, so let me explain what is variance inflation factor. Multicollinearity is typically checked using VIF statistics. VIF measures how much the variance of an estimated regression coefficient is inflated compared to when the predictor variables were not linearly related. What it means is, in our case, the beta coefficient of monthly income, when I just run a simple linear model between expense and monthly income, the beta was 0.3. But the moment I added annual income, the beta of monthly income became 0.6. So can I say that the beta is inflated? Can I say the beta is inflated? The question is how much it is inflated. The question is how much it is inflated. The way to find out how much it is inflated is called VIF. VIF measures how much the variance of the estimated regression coefficients are inflated as compared to when the predictor variables, when the variables that we are passing for the regression would not have been correlated. So the VIF formula is VIF is equal to 1 divided by 1 minus R squared. Here R squared is not the R squared of the model. Here R squared is the R squared of each independent variable. And how this R square is calculated? Can I build a model where I'll say monthly income is Y and rest all other independent variables are X. Theoretically, can I build a model? See, our objective was to build a model expense as a function of all X variables. For the time being, I forget expense. I'll take one of the X, X1, X2, X3, X4. There are 4 X. I'll take X1 and say this is Y. And I want to predict X1. I want to estimate X1 as a function of X2, X3, X4. Can I build a model? I can build a model. How good the estimate of X1 will be with respect to X2, X3, X4 is a question. It may be good, it may not be good. Agreed? Likewise, I'll now take x2, and can I have x2 as a function of x1, x3, x4? Likewise, can I have x3 as a function of x1, x2, x4 and x4 as a function of x1, x2, x3? Can I build those models? I can. Don't think whether those models will be good or not. But theoretically, can I build? I can. So here, if I build a model of monthly income as a function of number of family members, EMI, annual income, it may so happen the beta of this may come as 0. The beta of this may come as 0 and the beta of this may come as 1 divided by 12. Yes? Possible. I don't know what will be the beta's bit, but it is possible, right? So if I now get this as an estimate of it, can I compute R square of this model? Any model you can compute R square. If I get R square, which is say 0.98, what does this R square mean? If for this model I get a R square of 0.98, what does that mean? Well, it means that 98% of the variance in monthly income can be explained by this model, which is a function of family members, EMI and annual income. Yes? Similarly, I can build a model of family members as a function of income, EMI, annual income. And I may get some R square. That R square we know is coefficient of determination. 1 minus R square is opposite of coefficient of determination is called tolerance. 1 minus R square, which is opposite of coefficient of determination, is called tolerance. And the ratio of inverse of tolerance is called VIF. Inverse of tolerance is called VIF. Okay? The concept is simple. I have to find out, can one variable in the model be replaced as a function of other variables? So I can theoretically have monthly income as a function. If I build monthly income as a function of all other independent X variables. So in this case, what I'm saying is monthly income becomes my dependent variable. I'm not going to take expense. Expense is separate. I'm now going to take only independent variables. I'll take one independent variable and make it dependent, and all other independent I'll make them as, I'll take all independent variables. Of all independent, I'll take one variable out and make it dependent, and rest of all will remain independent. Now I am trying to make this dependent variable as a function of all others. I will get a model which may be good, bad, ugly, whatever, I'm not bothered. And that model will have a R squared. If the R squared is high, what it means, that independent variable which I made dependent can be predicted as a function of all other independent variables. And that can only happen if some variables are very correlated. If some variables are very correlated, only it can happen. If those variables are correlated, which means one independent can be completely expressed as a combination of certain other independents. And I don't want that to happen in my main model. So a high value of R square over here indicates there is a problem of multicollinearity. So high value of R square for any of these models indicates there is a problem of multicollinearity. So here we will not use the term R squared, because end of day R square will be computed, but to avoid confusion with the model R squared, there is a new term which is called VIF, and that VIF is computed. This model will have a R squared, which is how much of income could be defined, explained as a function of these variables. 1 minus R squared is called tolerance, and inverse of R squared is called VIF. So this calculation will give me, all these calculations will give me VIF for each of these variables. So I'll have a VIF for this, I'll have a VIF for this, I'll have a VIF for this, I'll have a VIF for this. Yeah. Once I have computed VIF for all the independent variables, I need to now interpret the VIFs. And the interpretation of the VIF is, if the VIF is equal to 1, which means there is no correlation. If the VIF is between 1 and 5, it means there is some moderate correlation. And there will always be some moderate correlation. But if VIF is greater than 5, which means there is some variables, there is a very high correlation. For example, in our case, the VIF of monthly income is 17, the VIF of annual income is 17, the rest of the variables have got VIF close to 1 only, which means they are not correlated by other variables, but these two have got some correlation, and I have to drop one of them now. To get this output, see, the concept is clear, the calculation is clear. Once the concept and calculation is clear, our codes are just 2 lines. What I have to do, I have to take my model, run it through VIF function, and that model will internally do all the calculation and give the VIF. So here, where is our multiple linear model? I'll have to run this again with all variables. Let me get that syntax. Yeah, here we have run all the variables, right? So this is my multiple linear model with all variables. Let me run that. And now this model, I'll pass it to the VIF function, which is of in package CAR. So first I have to load this package, library package I have loaded, and then I have to pass that multiple linear model to this VIF package. And when I run it, I get 17.73, 1.25, 1.02, 17.42. What is the interpretation? VIF equal to 1, not correlated. VIF equal to 1 less between 1 to 5, moderate correlation, greater than high. Okay, so this shows that this and this has got a correlation, and they are causing the multicollinearity problem. So one of them has to be dropped. So which to be dropped? Typically the variable which has got high VIF has to be dropped. However, in this case, I'll go with my business intuition. The business intuition is, because all the target variable expense is at a monthly level, so rather take monthly level income rather than take annual level income. So I'll drop annual income. And just coming to whether I can build a model or not, let's check that. Only thing what I have to do, all these steps we don't have to do. Please understand. M linear model, multiple linear model is built and we pass it to VIF. I don't have to do all these things manually. The reason why all these formulas have been shown, that in the background this is what is going to happen. That one of the independent variable will be made dependent and it will be regressed against all other independent variables. A model will be built, R square computed, and from R square VIF computed. All this is happening in the background. We are not supposed to be bothered of it. But anyways, let me show you. So I could have done, say, I'll call this as a VIF monthly income model. Let me just name it. So if that is the case, income will become my dependent variable. So income becomes my dependent variable, and I am now having it as a function of all other independent variable. So annual income also has to be there. Let me take this annual income also. Plus this. Okay. So tilde is basically I am now making monthly income as a function of family members, EMI, rent, annual income. Yeah. I'll build this model. Let me see what is the R square of this. So summary VIF underscore monthly income model. What is the R square of this? 0.946. 0.9436. What is the calculation? Tolerance is equal to 1 minus R square, 0.9436, and VIF is equal to 1 divided by tolerance, inverse of tolerance. 1 divided by VIF 17.7. Yeah, 17.73. Very close to that number. Are you getting the point? In the background, all these combinations is happening. Why is this combination happening? Because what it shows is the equation that it has developed, 5.82 e raised to 2. So 582 times number of family members plus 0.13 EMI plus 0.078 times annual income is the relationship between this monthly income and the other variables. And based upon that equation, monthly income can be computed for a given family. Right? That's the entire thing. So likewise, all variables internally, independent variable with respect to all other independent will be regressed, R square computed, 1 minus R square, 1 inverse of that. And you get VIF. Only thing what we have to now do is interpret this VIF and take a call. Any VIF which is greater than high, drop that variable. So here I'll not drop both. I'll drop one. Okay. So here, because I now know that annual income and this has got relationship, my final model will have only these variables. Expense as a function of monthly income, EMI, family members, and this is what I'll have as a final model. Now let us again see summary of that final model. Summary M underscore linear mod. We started with R square of 42%, 0.42, which means 42% of the variance in expense could be explained. Then we changed and made it two variable model. We added family members, and from 42 we moved to 57 something, 0.57. Now I'm making three variable model. From 0.57 I'm moving to 0.69, which means 70% of the expense can be explained. there's still 30% of variance which is not explained. And whenever you build a model, your attempt should be try to explain 80-85% of variance maximum. R square should go up to 0.8, 0.85. Rarely you will be able to go with 90. If you have achieved 80-85%, we are not supposed to do 100%. If it goes 100%, which means each and every case you are able to predict correctly. Okay? Which is not possible. Make sense? Because there is some aberration in every individual. Individual's behavior is not, see, the behavior is not if else behavior. If this condition is matched, then this will happen. Else, if this condition is matched, then this will happen. It's not that way. It's a probabilistic element. It's not a deterministic. The problems that we are trying to solve are not 100% determinable. Right? So some amount of thing will still remain unexplained, and that is called residual error or residual noise, whatever you want to call it. Now there is one more important aspect. Here there is a multiple R squared and there is an adjusted R square. When you build models, as you keep increasing variables, the R square, multiple R square will keep increasing. If you add a variable which is useless variable, which has got no value, no importance, and if you use that variable also to build the model, so I have now three variables: monthly income, EMI, number of family members. Assume I have one more fourth variable, and that fourth variable is, say, household flat number. Gender can still impact expense. But let's say I've got a useless variable, household flat number. And assume this 50 members are from the same society. And again, that society has not an n level of towers. Someone may say, sir, household flat number is also important because if it is 10th floor, they are more rich compared to someone who is at the first floor. So let's say even assume that is not there. It's all of them are and in the same row. Is the household flat number of any importance? No. If I bring that household flat number, assume these 50 have got flat numbers as 1, 2, 3, 4, 5, 6, 7, 50. And if I bring that variable, you will see multiple R squared still improving. Okay, so let's do that. I'll explain the multiple R square. It is still going to improve. So what I'll do is, our data is income expense. So dollar flat number, okay, is equal to, because I know there are 50 observation, I'll create a vector of 50 and directly assign that values. Yeah. So let us just do view income expense. So a new row, flat number has got added. Values are 1, 2, 3, 50. Yeah. Now I'll add this. This was my model, final model, but I'll now add this variable also. Okay. Now I'll build the model and let me see the summary statistics of this model. R square has become 0.7022. What was my previous R square? 6978. 6978, marginal improvement has still happened. I'll add another variable. Not name of society, say, no, let me add can I have a random numbers R unif, right? R unif. Let me just understand this function. What are the parameters to be passed? What are the parameters to this? Or probably, okay, what we'll do is we'll flat number square. Okay, I'll just add one more variable, income expense dollar flat number multiply income expense star flat number, but again this will become multicollinear. Multicollinearity will come, multiply income expense star no, but anything that you do, it will be multicollinearity, because you are able to create. I want a random number generation. Let me get the syntax. So let us generate this random number using RUnif. We are generating 50 random numbers. Okay, let us quickly view this data. So I got a random number here, right? So now let us build this model further. Where is that earlier model? This was the model. So here I added flat number. Now I'm going to add a random number also as a parameter. Let us see this model. Model is built. Let us see this model. Summary. R square 0.7055. What was the previous R square? 0.7022. So now it has become 0.7055. Point I am trying to make is, each new variable you keep adding, I can add some more 50 variables and get this R square going up to 0.8 also, 0.85 also. And then you will say 80% of the variance has been explained. 85% of the variance is explained. That 80%, 85% of variance is of no use now. Yes? So when you go to multiple linear models, you are not supposed to see R square, you are supposed to see adjusted R square. Now if you see the adjusted R square of this model, 0.67, I added one more junk variable, 0.6721, and that was 0.6757. Actually, adjusted R square has gone down instead of increasing. Let us see the previous model. It was 0.6781. The moment I added flat number, adjusted R square has gone down. So adjusted R square, the concept of adjusted R square is, if the incremental variable is not adding to the estimation efficiency, correctness of the estimates, the adjusted R square will drop. The incremental effect, it is going to bring it down. Okay? And that's the reason adjusted R square is the right way to see. So that when you build a model, if you add a new variable and you have to decide whether the new variable is a good variable or not, what you should do is, you should see the previous model's adjusted R square, then run the regression again with the new variable added, see the adjusted R square. If adjusted R square does not increase significantly, if there is a minor increase, say that R square could have, it would have happened that R square earlier was 0.678 and now you added one more variable, and adjusted R square has increased from 0.678 to 0.680. The increase is 0.002, insignificant. Then you can take a call that this variable is not bringing any additional information. So that variable should not be part of your model. Yeah, this is the concept of adjusted R square. Yeah. So my final model will be not having these junk variables. Multiple R squared, adjusted R squared. So with this, your linear model is completed. The final statistics that you have to see is adjusted R square, p-value. P-value says this model is significant. Overall, the model is significant. Adjusted R square says that 67% of the variance in your target variable is explained. 30% variance is still not explained. If that 30% of variance has to be explained further, then probably you may need additional variables. For example, locality. Someone staying in a posh locality, someone staying in an average locality can impact the expense, right? So locality. Distance from station or distance from public transport system. Yes. So the point is the additional expense that a person household incurs can be explained. For example, additional variable could have been age, average age of the family members. If all are youngsters, medical expenses will not be there. But if there are youngsters and old age people, or if there are youngsters and kids, again family expenses will be there, right? So there is some additional information which is not there with us, which can impact the event that we are trying to predict, and that if we have that variable, then probably my R squared can further be improved. I hope now this concept of coefficient of determination is very clear. Yeah. So that is R squared. Now one final thing. When you build a linear regression model, there are certain assumptions which are made. Frankly speaking, when we nowadays build models in data mining, we keep aside these assumptions. We don't even test it. But one of the key assumptions in a linear regression model is the error term should be homoscedastic. What is homoscedastic? Homoscedasticity simply means that if I compute variance of the error term across observation, then it should be same. What it means is, this is my X, this is my X, this is my Y. I've got these various dots are data points. On these dots, which are data points, I built a model. When I built a model, this is the linear equation I got. And based on that linear equation, for all values of X, I am able to predict Y. But this is the error. This error at any given value of X, if I cut it here, then the error variance, I can compute variance of error also. See, variance is what? X minus X bar the whole square divided by N. If I take all the error terms in that Excel, if in this Excel I take this error term, can I compute variance? Right? I can compute variance. If I cut this data for all values of x which is 10,000, can I get all values of x which is 10,000 and get all the error terms? Can I compute variance only for x equal to 10,000? Similarly, can I compute variance for x equal to 18,000? So that's what I am saying, that if I cut at any given point and then compute the variance for the error term, it should be same. This should be same. In that case, it is called homoscedasticity. Okay. If this error is not same, here you see that the curves are different. What it means is that linear model may predict values more correctly at one place and it will predict less correctly at other. See here, if you see, this linear model is predicting values more correctly in this zone. Yeah. Whereas here, there is a wider spread of error. Yeah. So when there is a heteroscedasticity, you have to ideally build multiple models. What it would mean is I should build one model for this much part of data and I should build another model for this part of data. Let me create that kind of a visual scenario and you will be able to better understand it. Assume my data is spread out like this. This is how my data is. Your model, linear equation model, will actually go like this now. On the contrary, if I could have split this data into two, one is this and other is this, and I build a model, this linear equation would have gone like this and this linear equation would have gone like this. The two model solution would be a better solution. Agreed? So if there is a heteroscedasticity in the error term, in that case, building one linear regression model may not be a right solution. Probably a linear regression model may not be able to solve the problem, or if you want to still use linear regression, then you may have to build multiple linear regression models. The basic assumption in linear regression is data should be normally distributed and error term should have homoscedasticity. Frankly speaking, these assumptions many a times we don't even test. We simply take the data, build a model, and if we get a R-square of 0.7, 0.8, we'll say, okay, we have built a decent enough model. It is quite possible by splitting the data into two segments and then building a separate models for them could have led to R-square of 0.85, 0.88 for both of them. Yeah. So in our data set, which I have given 50 data points, income and expense data that I have given, just see whether there is a heteroscedasticity, and if yes, would it help to build a separate model for high income segment and a low income segment. What cutoff you take for high income and low income, I leave it up to you. Yeah. So with this we complete linear regression. Any specific questions that you have? For time series forecasting, typically I will go with time series forecasting type of models and ARIMA models. I would not go with the linear model. So the question what you're saying is whether I have the data structure available before I go into the model development. Definitely before you go into the mining step, the data structure has to be provided. Okay. So the team, whoever is providing you data, typically the way we start off is we do full data understanding. All the variables that I have, I should know that variables before I start with any analytical step. So those are basically exploratory data analysis steps. Each variable you will try, understand, assimilate, and then you will try to make hypothesis statements that my target could be impacted by this variable and this is how it would be impacted. So those things has to be available and your hypothesis should be created. Any other questions? So the question is why VIF is required when I'm going to do data understanding before doing model development. Let us take this simple case. Here, where is the collinearity correlation table? This is a correlation table which I have got. Assume this correlation which is between, okay, here I have not put annual income. Let me go to my code. Let me quickly run that. Core Inc expense. So we have got annual income and monthly income correlation 0.97. Assume this correlation does not come 0.97, it comes 0.62. In this case it was perfect correlation. And there is another component of income which is given to you saying joining bonus. Okay. So annual income will be a function of 12 times monthly income plus joining bonus or plus year-end bonus. Assume there are two more variables. Annual income is equal to monthly income plus joining bonus plus annual performance linked bonus. And because of that, annual income and monthly income correlation is only 0.6. Annual income and joining bonus has a correlation of 0.7. Annual income and annual performance linked bonus has got a correlation of 0.35. Okay. By just seeing correlation, you may not be able to arrive at the equation annual income is equal to monthly income plus joining bonus plus performance bonus. Can you arrive at equation if that is the kind of variables? Just because I'm giving variable names which are sensible, you can say I can arrive it. But don't think so all the variables that you get are having such sensible relationship. There is a variable x3 which is equal to x2 plus x1 minus 3 times x5. Assume that is a variable. When you do x3 versus x2, it may not show correlation. When you do x3 plus x1, it may not show correlation. When you do x3 minus x5, x3 with respect to x5, it will not show correlation, perfect correlation. but x3 is still derivable as a combination of x2, x1 and xy. Agreed? Independent correlation between them is not going to show correlation. Now how do you find that x3 is possible, x3 can be derived from x2, x1 and xy? Are you going to write your own equations? What Vif is doing internally, Vif is trying all combination, taking one independent variable, making it dependent, and then regressing it along all others. If there is a relationship, automatically that equation will get formed, right? And the moment x3 is predicted as a combination of multiple variables, Vif of x3 will go to become very high. You can immediately see that x3 can be predicted from other variables and x3 should be dropped. And that cannot be done from simple correlation table, and that cannot be visualized just by our understanding of one variable at a time, basic exploratory data analysis. These interaction terms between the variables, we cannot keep thinking everything here. Make sense? So if there are no more questions, then probably we'll call it end of our session on linear regression. I would suggest that try doing some more exploratory work on linear regression to understand these concepts better, because one of the technique that we are going to learn is logistic regression. Logistic regression is nothing but a linear regression only, but it's a transformed kind of a linear regression. So again, these concepts will be there in logistic regression technique also. And logistic regression technique is one of the most widely used technique in predictive analytics. So it would be good that you can, if you can practice and revise the linear regression concepts. With this I'll call it end of our session. Thank you.